Hello everyone, I'm very excited to talk about our lower bounds for non-adaptive local computation algorithm. This is a joint work with Amir, advisor Sohail, and Madhu. Let's just start with defining LCAs. The model was introduced by Ronnie Tamir Vardiji in 2011. This setting is particularly interesting when both the input and the output of our problem are large. So our goal would be to only look at a fraction of the input and compute a part of the output as well. Let's just start with some examples. Assume we are given a specific vertex V. We want to figure out whether this V has an edge that appears in maximum matching or not. To do so, we will only look at close vertices to this vertex V and decide if we're adding an edge from this vertex to matching or not. And we're not computing the maximum matching for the whole graph. Another example is vertex coloring, where we will only output the color assigned to the vertex and not the colors of the whole graph. So more formally, you're given a graph G and a prompt V in the vertex set, and the algorithm can query any vertex U that it has its ID. So let's say we start with vertex V, then the algorithm can query this vertex, and also it could retrieve its neighborhood. So when we are starting with vertex V, the algorithm looks into the neighborhood of that vertex, and then it potentially could adaptively choose look at the other vertices and decide which one it wants to query next. So let's say the algorithm decides this vertex here and continue doing that until it can give an answer for the problem for the particular vertex that we prompted. There are two main properties that we want an LCA to have. One is that we want it to be consistent, meaning that different answers to prompted vertices should collectively form a single valid output. And also we want it to be historically independent, meaning that the prompts should not affect the future outputs. We can think of it as local outputs coming from a fixed global output. In the non-adaptive setting, you can think of as these queries to vertices to be picked non-adaptively instead of the algorithm looking into the vertices that it observes and deciding which one it wants to see the neighborhood next. Instead, we want the algorithm to decide beforehand what is going to be the structure of the tree that is going to open. So more formally, a non-adaptive algorithm would specify a single tree rooted at the prompted vertex V, and then using that, it would explore the neighborhood of V. An example here is a path of length 3, and you can think of it as the prompted vertex picking a random walk of length 3. And it will only look into these observed vertices to decide on the output. And as you can see, for any prompted vertex, the structured tree is going to be the same for a single LCA, non-adaptive LCA. This structured tree could be a two-array tree or a multi-array tree that would fix depth R, and the prompted vertex would look at all of the R hub neighborhood of itself to decide on the output of the algorithm. Let's now take a look at adaptive versus non-adaptive LCA. Parnas-Ron proved that an R-N distributed algorithm would imply a non-adaptive LCA with delta to the R query complexity. Let's define distributed model. In short, well, in each round, a node can send unlimited messages to its neighbors. And the goal is to spend as few rounds as possible to come with output to the problem. What that means for our non-adaptive LCA is that we can look at the distributed algorithms known and come up with non-adaptive LCAs. So there is a constant approximate mean vertex cover that needs log delta over log delta rounds in the distributed setting that would imply a non-adaptive LCA with query complexity of delta to the log delta over log delta. In the adaptive setting, there are LCAs that obtain constant approximate mean vertex cover with polydelta queries. And as you can see, there is a huge gap between these two. And we want to know whether we should actually care about designing more efficient non-adaptive LCAs or this gap is actually necessary. Before answering these questions, let's see why we should look into non-adaptive LCAs. The first thing is that adaptivity has been studied in property testing. Another use case is the MPC model. We proved that if non-adaptive LCA were as efficient as adaptive ones, we get exponential improvements over MPC algorithms. Let's get into our result. We proved that Parnas-Ron reduction is actually optimal for max matching, maximum independence set, and mean vertex cover. And the complexity of non-adaptive LCA is actually delta to the log delta over log delta. So more formally, we prove a lower bound that for any non-adaptive LCA that returns a constant approximation for any of these three problems, that would require delta to the log delta over log delta queries. Now we'll talk about some intuitions of how this theorem would look like, how the proof of this theorem would look like. And for that part, I would focus on max matching problem. Let's go back to the Parnas-Ron reduction. They prove an all-round distributed algorithm would imply a delta to the R query non-adaptive LCA. So if we prove a delta to the R query lower bound for non-adaptive LCA, that would imply an R round lower bound in the distributed setting. Now, to find out the ways to prove lower bounds for non-adaptive LCA, it makes sense for us to look into the methods used in the distributed setting. So let's do that. The first method is round elimination. If you have a problem PR that needs R round algorithm, distributed algorithm, then that would imply an R minus 1 round algorithm for a slightly easier problem, PR minus 1. And if you continue this, you would get a 0 round algorithm for non-trivial problem, P0. And that would be a contradiction. And this is the way that they use round elimination to prove lower bounds. The problem is that we don't have a clear notion of rounds in non-adaptive LCA, so we cannot actually use this method. The other method that is widely used for proving lower bounds in distributed setting is constructing a family of graphs where two vertices, for example here V and U, that produce different output to our problem actually have isomorphic R-hop neighborhood. What I mean by isomorphism here is that you can correspond the vertices, so the corresponding vertices have the same degree. The Cohen-Mascobroda-Wattenhofer paper in 2016 used this method and proves the log delta over log delta lower bound on the round complexity of distributed algorithms that compute a constant approximate mean vertex cover. But there is a problem here that we can easily apply these constructions, use this construction for non-adaptive LCA. And that is for non-adaptive LCA, you can use as much as delta to the R query. So you could potentially have a path of length delta to the R, and that would exceed the R-hop neighborhood of the vertices that we wanted to distinguish V and U. And it might be that the algorithm could see these paths and distinguish between them easily. So if we go as low as one hop further from these R-hop neighborhoods, the lower bound breaks. So we need something more than these constructions that have isomorphic R-hop neighborhoods. So let's see what lower bound techniques we need for non-adaptive LCAs. We will combine techniques of distributed lower bound and their constructions and sublinear time lower bounds. We will build on top of the distributed construction of KMW. We'll need to modify it. And we follow the recipe of Sohail, Mohammed, and Aviad for proving sublinear time lower bounds. First, we need to change the construction to show that there are no cycles. And after that, we'll couple paths with the same degree sequences of size at most delta to the R that start with our vertices V and U that produce different outputs. So instead of only looking at the R-hop neighborhood, we need to actually couple any path of length delta to the R. We are using the recipe of BRR, but the coupling of these paths, we are doing them in a completely new instance of KMW, and we also need to modify this construction so that this coupling works in it. So these are the main challenges that I'll get into in a bit. Before that, let's get into what is actually the construction of KMW. They have this instance that they call a cluster tree. Each one of these clusters is a set of vertices. What we care about is the degree of the vertices. That is what is going to help us to be able to distinguish between two vertices when starting at V and U here. So the degrees here are such that the colored nodes all have degree delta and white nodes have smaller degrees. So if you see a colored node and a white node, then you can distinguish between our starting vertices V and U. These are the vertices that we are going to try to distinguish. One of them is from cluster C0 and one is from cluster C1. Another thing that we need to know about this construction is that cluster C0 is large. What KMW prove is that R-hop neighborhood of V and U are isomorphic, where R is log delta over log delta. And the way they use this isomorphism for matching is as follows. They would copy the construction, add a matching between the corresponding vertices. And we know that since C0 is large, there is a lot of edges here between the C0 clusters that an algorithm should be able to find if it's giving a constant approximate matching. Now, if the algorithm is starting at some vertex W here, it needs to distinguish between edges between C0 clusters and the edges here between C0 and C1 clusters. So we call these misleading edges, and the edges between C0 clusters significant edges. So an algorithm should be able to distinguish between these misleading edges and significant edges in order to find a large matching. For this, we need to actually distinguish between a vertex V in C1 and a vertex U in C0. And since they already proved, Pavlov proves that these two R-hop isomorphic neighborhoods that imply an R-round local lower bound in a distributed setting for this problem. So now let's see what happens when we try to use this construction to prove a lower bound in non-adaptive LC. Well, as I mentioned, if we go as low as one hop further, these two, the R plus one hop neighborhood of V and U are not going to be isomorphic. So if you look at these red path and blue path here, the red path is going to end up in a colored node, and a blue path is ending up in a white node. And since they have different degrees, you can distinguish between V and U using an R plus one length path. What we need to prove is that although these paths exist, it is really hard for a non-adaptive LCA to find this path and go to the right direction at each step. So this is what we are going to prove in order to get a lower bound in non-adaptive LCA setting. Well, first of all, we're going to change the construction of KMW. We will add a set of dummy nodes that every vertex in the construction of KMW has constant fraction of their edges to these D set, the dummy set. We prove that any path of length log squared delta will end up in the dummy set. This is because at each step, there is a constant probability of going to the dummy set, and therefore, after log squared delta steps, with high probability, these paths are going to end up there. And once we get to the dummy set, we can actually couple the path perfectly from there on, because we lose information of whether we started from C0 or C1. So yeah, after getting to the D set, we can couple the path perfectly, and the coupling would not break after seeing the D set. Remember from the main lemma of KW that log delta over log delta hop neighborhood of U and V are isomorphic. So if we take a random log of this length, we will not be able to distinguish between U and V. And in the last slide, we showed that random logs of length more than log squared delta are also not distinguishing U and V because they enter the D set. It remains for us to prove random logs of length between log delta over log delta and log squared delta also have a very small probability of distinguishing. The way we do this is to quantify how close a path is to revealing useful information. And a useful information would break the coupling. We'll identify some of the edges that bring a path closer to distinguish between U and V, and then we bound the number of these edges in each step, and that would bound the probability that the path would traverse one of these edges. And that's how we proved the lower bound for non-adaptivity. That was the last step. Before ending the talk, I want to mention some open problems. Well, in this paper, we introduced the notion of non-adaptive LCA, and it's interesting to look into the complexity of non-adaptive LCA for other problems such as vertex coloring or edge coloring. One of our results was proving that Parnas run reduction is optimal for matching vertex cover and MIS. Another problem is that whether it is possible to improve over Parnas run reduction for other problems. Again, vertex coloring or edge coloring can be improved over this reduction or not. Thanks for listening. This is the end of my talk.